Hi students, we met again online. After thinking a while, I think that there's quite a content for the quadratic form and principal access theorem. That's why I decided to make this about 30 minutes short videos, I hope. So let's continue from last Wednesday. So last Wednesday, we defined a quadratic form using a symmetric matrix, where Qx is equal to S transpose multiplied on A and multiplied by X, where we will get a polynomial in Xi. We have run through examples, first examples using concrete symmetric matrix A and B to get the desired quadratic form. We observe that in B, which is the diagonal terms, the terms that appear inside the quadratic form are just square of variables. Okay. While if we have off diagonal non-zero term, then the cross product term will appear. Similarly, we can work backward from the quadratic form to find the symmetric matrix that define the quadratic form. Okay. And we have seen some examples, nice picture here, seeing how this cone gets sketched given a quadratic form. Okay. Note that the quadratic form here are all squared of a value. So if we were to substitute x1, x2 by a number, you always get positive number. Okay. So for example, 3 times a positive number plus 7 times positive numbers is always positive. But at the 0 point, you will get 0 plus 0, which is attained by this cone here. Right? For example, D, C, and B, we will all have the 0 point. But notice that B has more 0 point than the rest, where along the x2 axis, it is all 0. While for this saddle on part C, there's only 1 0 here. And similarly for D, there's only 1 0 in the graph. You can see that some of the graph is always greater or equal to 0. And some of the graph is always less than or equal to 0. While some of the graph is a mix of greater than equal to 0 and less than equal to 0. And some graph has more 0. Okay. So we have defined, classified the quadratic forms in a few ways. If Qx is greater than x for all x not equal to 0, then we call it a positive definite. If x is less than 0 for all x that's not equal to 0, we call it a negative definite. We call it indefinite if Qx assume both positive and negative values. And we call it positive semi-definite if Qx is greater or equal to 0 for all x, and negative semi-definite if Qx is less than equal to 0 for all x. So the example of positive definite would be something like this. Since for non-zero x, it is all positive. Second example here is negative definite because for all non-zero x, it is less than 0. Okay. And similarly, if Qx assume both positive and negative values, it is indefinite. For example, this saddle here. Okay. For the first example, it is also positive semi-definite. since it is greater or equal to 0 for all x. Second, for the second example, it is also negative semi-definite since it is less than or equal to 0 for all x. All right. So you can determine for yourself what are these four pattern belongs to. I'll write it in the lecture notes later. Okay, so how do we classify quadratic form in general? It might seem very hard. So we need to devise some method to see it easily. So let's look at one example. Okay, let's look at this example here. To make a change of variables to transform the quadratic form qx into x1 squared minus 8 x1 x2 . Okay, let's look at this example here. Make a change of variables to transform the quadratic form qx equals to x1 squared minus 8 times x1 times x2 minus 5 times x2 squared into a quadratic form with no cross product terms. Okay. So let's write qx in terms of symmetry matrix, right? So suppose qx is equal to x1 squared minus 8x1 x2 minus 5x2 squared. Okay. Recall that to find the symmetric A, the coefficient of the diagonal term should be the coefficient for x1 squared and x2 squared. For example, we have 1 and minus 5. And for the term of x1, x2, the coefficient will be split into two parts here. Split equally into two parts, which we get minus 4 and minus 4 on the off diagonal side. You could check that really when you take xt multiplied by a multiplied by x, you actually get the desired quadratic form. I urge you to check it yourself so that you can try it out and figure out how I exactly see my matrix, see the symmetry matrix A. Okay, the next step is we can diagonalize this matrix, right? So by theorem, we know that A is orthogonally diagonalizable if and only if A is symmetric. Okay, so since for quadratic form you always get symmetric matrix, it is always diagonally diagonalizable, orthogonally diagonalizable, sorry. So let's compute the determinant of A minus lambda, which we get 1 minus lambda and minus 5 minus lambda on the off diagonal and on the diagonal and off diagonal we get minus 4. Let's compute the determinant of this matrix here, where we get minus 1 minus lambda times minus 5 minus lambda minus 16. Okay, so let's expand it out, which is 4 lambda plus lambda squared minus 16, where we get lambda squared plus 4 lambda minus 21. Okay, so in this case, we can factorize it into lambda plus 7 and lambda minus 3. So we see that the eigenvalues of A are minus 7 and 3. Okay, which is looking by finding the root of the characteristic polynomial. All right. So next, what should we do? So we should find the eigenvectors. So for eigenvectors, for lambda equals to minus 7, we first find what is A plus 7i. Okay. So what is A plus 7i? We'll get 8, 2 on the diagonal, and minus 4 on the off diagonal. Then we'll try to row reduce this guy here, which we then get 8 minus 4 and 0, 0. After further row reducing, we'll get 1 minus a half, 0, and 0. All right. So where we find the eigenvalue for lambda equals to minus 7 is 1/2 and 1. Okay. So how about eigenvalue for lambda equals to 3? So we'll compute A minus 3i. Okay. What is A minus 3i? So A minus 3i is minus 2 and minus 8 on the off diagonal on the diagonal, and the off diagonal we have minus 4 again. Okay. So after row reducing, we will get minus 2 minus 4 on the first row, and then we will get 1 and 2 on the first row. In that case, our eigenvector will be minus 2 and 1. Okay. All right. So you could observe that these two are orthogonal to each other. Right. So what's the definition of being orthogonally diagonalizable? Right. Let's look back to the book or the lecture notes. So it is orthogonally diagonalizable if it exists a orthogonal matrix such that A equals to P D P inverse. Okay. So what you could do is you could normalize this vector further to get the normalized eigenvector. Okay. So you will take V lambda equals to minus 7 divided by 8 lengths. Okay. What is the length of V lambda minus 7? Okay. So we should do the computation. which is 1 over of V lambda equals to minus 7 inner product with X of multiplied by V lambda again, where we get 1 over 4 plus 1 times 1/2 1. Okay. And remember that there's a square root for length. Okay. So what do we get? So we get, actually, let's make the space more. So what do we get? We get 1 over square root 5 over 4 times half 1. Okay. Which is what? Which is 2 over square root 5 times half 1, which is equal to 1 over square root 5 times 1 and 2. All right. So this is one of the unit vector. So similarly, sorry about that. Let me adjust a little bit. So similarly, you could do the same for v equals to lambda 3. Okay, let me move it up. Make some more space. Let's make the whole thing smaller again. All right. So what is v lambda equals 3 over x length? Okay, let's compute x length. All right. So the length is actually 1 over square root 5. Okay. Okay, so what's next? So this means that we can take P, so let P equal to V lambda equals 7 over x length, and V3, V lambda equals to 3 over x length after normalizing. Take this as the columns of P, then this is the P that will orthogonally diagonalize our matrix A. Okay. All right. And D, which is the eigenvector, which is 7 and 0. All right. So then A is equal to PD P inverse, or equivalently PD P transpose, since P is an orthogonal matrix. Right. So in this case here, what can we do? So next, since Qx is equal to x transpose A x, we can substitute our A into the equation, where we get A equals to PD P transpose x. Okay. So what we can do is we take x P, so we can combine So we can combine these two terms into PTX transpose T. PTX. So in this case, instead of conjugating instead of having X transpose and X on the right of A, we turn A into a diagonal matrix where the vector become P transpose times X. And this is what we call a change of variable. So we can make a change of variable to Y so that it is still in the form of a quadratic form. Okay, where Y is equals to P transpose X. Okay. So we can see that what is the desired result here. So if Y equals to Y1, Y2, okay, then what we get is Y1, Y2 transpose multiplied by D, which is the diagonal matrix, and multiplied by Y itself. What do we get? Let's see what do we get. We'll get 7Y, 3Y2, and we get, sorry, this is already transposed, so we will remove the symbol T. We'll get 7Y1 squared plus 3Y2 squared. Okay. So under this change of variable matrix, change of variable, where the change of variable matrix is applied on X, then we can transform our QX into a term without, into a formula without cross product. Okay. And notice that this coefficient of the square of y1, y2 is actually coming from the eigenvalue. Okay, notice that I copy the eigenvalue down wrongly. So the eigenvalue here is actually -7. So let's change it. So there's a -7 here, and a -7 here and here. Okay. All right. So what's this actually really about? So let us bring out the theorem. The principal axis theorem. So let A be an n by n symmetric matrix. Then there's a orthogonal change of variable where x equal to py that transform the quadratic form S transpose AX into a quadratic form, another quadratic form, Y transpose dy with no cross product terms. Okay, only square of variables appears. The columns of P are actually called the principal axis of the quadratic form. Sorry, let us zoom in a bit. S transpose AX. The vector Y is the coordinate vector of X relative to the orthonormal basis of Rn given by this principal axis. Okay. So normally, if we look at this quadratic form when it is equal to 1 and A and B are greater than 0, we will usually get a circle or ellipse, depends on A and B we have. And we will get hyperbola if we have a minus in the middle. Okay. So what's y2 and y1 about is about the principal axis of this, we'll call it a conic section. Okay, it's a conic section here. So it's about changing this y1 and y2 into the right position so that we can get a diagonal terms. All right. So for this one, we will make it a homework and I will provide solution later. Okay. So the key things why we make it into this, make it all into the square terms only, is because in this way, we can easily determine a quadratic form is whether positive definite, negative definite, indefinite, or positive definite. Okay. Let's look at this result here. So there's a theorem here. Let A be an n by n symmetric matrix, then the quadratic form is either positive definite if and only if all eigenvalues are positive, negative definite if and only if all the eigenvalues are negative, indefinite if and only if A have both positive and negative eigenvalues, positive semi-definite if and only if all eigenvalues of A are non-negative, negative semi-definite if and only if all eigenvalues are non-positive. All right. So, why is it true? So let me demonstrate to you why is it true. So let me make another page. So this is not relatively hard to see. Okay. So by the principal access theorem, given a quadratic form, okay, where A is symmetric, okay, really we can orthogonally diagonalize A such that A is equal to P D P transpose, where P is an orthogonal matrix and D is a diagonal matrix. All right. So really, I haven't touched on what is principal axis theorem first, but what we know from principal axis theorem is we can substitute A back. We can substitute PDP in transpose back to the quadratic form. Sorry, I missed out this a little bit. It's S transpose X. Okay. So it's really PDP, sorry, PDP transpose on here, and then here X. Okay. So we can make a change of variable such that PX transpose multiplied by P transpose inside and PTX. Okay. So this is the where Y equals to PDX is the change of variable. Okay. So in this case here, we will see that actually this split out into y1 times y2 squared, y2 lambda 2 y2 squared, all the way up to lambda n y squared. Okay, where the lambda I are the eigenvalues of A, right? So you could see that the eigenvalues will basically control the value of Qx, since y1 squared, yi squared are always positive. Okay, let me write down what I'm saying. So since y1 squared, yi squared are always positive, the eigenvalues lambda I are controlling the value of Qx. So if you could imagine that all lambda I are negative, then you will get a negative semi-definite quadratic form. If all the lambda are all positive, then you will get a positive definite Qx. Okay, so let's return to the example. So by the theorem we've seen just now, you can see that all these quadratic form are only contain yi square term. There's no cross product term inside here. So these coefficients are actually the eigenvalue of the respective symmetric matrix. Since these two are positive by the theorem just now, this quadratic form is actually what? It is actually positive definite. By the theorem we have proven just now. Okay. And it is also positive semi-definite. All right. This is similar to B. Okay, B has also only positive eigenvalue. So both of these cases have the same classification. How about C? Okay, since one of the eigenvalue is positive, the other is negative, so there's a mix of them. So it is indefinite. How about D? D are both negative, so it is negative definite. On the other hand, it is also negative semi-definite based on the classification and the theorem. Okay, all right. How about this question here? Can you determine whether that this quadratic form is positive definite, negative definite, or indefinite? Can you see from the coefficient here? Maybe you will see that all of the coefficient is positive, but be careful that there's a cross term here. Right? Cross term might produce a negative values. Really, you need to first diagonalize it, the symmetric matrix that define this quadratic form, and then look from there. Okay, so first try to find the eigenvalues that define the quadratic form. What do you mean by that? Because the quadratic form is defined using a symmetric matrix. Okay, so what's the symmetric matrix we are looking for here? Okay, so looking at the squared term, we can make the coefficient into the diagonal entries, and we will split them equally into the right spot. For example, we have 2 on the first off entry, and then another 2 on the second off entry. Okay, so by the previous theorem, what should we do? We should use the eigenvalues to check whether which classification of quadratic form lies into. Okay, so it turns out that after calculating the determinant of a minus lambda I, so make sure you can write it out, this part. I work it out. It turns out 5, 2, and minus 1 are the eigenvalue of A. Okay, so you can see that some of the eigenvalue are positive, some of the eigenvalue are negative. Then by this theorem here, we can say that it is a indefinite quadratic form. Okay, so Q is an indefinite quadratic form. Okay, that's all what I want to say about quadratic form, classification of quadratic form, and principal access theorem. So if you have more questions, please email me, message me tomorrow, see me in my office hour. Bye for now. Thank you for watching.